All right. So which ones do you want me to go over?
4 and 5 on the back.
4 and 5 on the back.
Just 4.
Okay. So here's the setup on the problem with the cliff dive. So they run along, right? And they turn into a limit. Okay? So let's talk big picture. So as soon as they leave the cliff, what do we assume happens to their Vx?
It stays constant.
Stays constant. We're assuming that there's no forces acting horizontally, therefore there's no acceleration horizontally. So whatever Vx they have at the beginning is whatever Vx they have at the end. Okay? Because what happens in the x stays in the x. What happens in the y stays in the y. So there's some cliffs out here, or some rocks at the base of the cliff, right? You want to make sure that you clear these, because if you don't, that would be a one-time mistake, and one time only. Okay? Now, you're told that the cliffs are 41 meters high. So right away, since this is a limiting problem, knowing the 41 meters, what can you find right away? I can find time. Okay? So I can sit here and go, okay, well my distance traveled is 1/2 at squared plus v naught time. Now, here's what you have to be, Josh. So here's what you have to be careful of. If you're going to use your gravitational acceleration, and this is a limiting problem, what's the value of this v naught? 0. Even though they're running when they jump off, their initial vertical velocity is 0, so I don't have to worry about this. So then I go, oh, 2x over a, take the square root of that, boom, there's my time. So that's going to get me the time that they're in the air. And it doesn't make any difference if they just walk to the edge and go whoop and fall straight down, or if they run off like this. Because look, what's the only thing that determines how long they are in the air? Two things. How far they fall and gravitational acceleration. The color of their swim trunks doesn't matter. Can't plug that into the equation. Okay? There's any number of things I can't plug into this. Did I give you the mass of the diver?
No.
No. You know why? Doesn't matter. Okay? So this allows you to get the time. Now, you know the horizontal distance that they have to be from the cliff. This is your range. Okay, that's how far they have to go. And that range, because we're assuming that the horizontal velocity is constant, is Vx time. Here's your time, you know the range, find your Vx. Now, that answer should be between like 4 and 5 meters per second, okay? Which is reasonable. If that answer had worked out to be like 11, let me give you a hint. Don't go cliff diving because you can't run that fast even if you're a world-class sprinter. Even at 4 something, that's a pretty good clip. Okay? So you just can't like walk up and go, okay? Bad. You can do that, but you only do it one time. Okay?
So between 4 and 5?
Yes.
Alright. So
I got that one.
Okay. So which one?
5.
5. Okay, with the dart? Okay. So there's the dart. Stop it. Okay? So as soon as the dart leaves your hand, what does the dart start to do?
accelerate.
It begins to accelerate and it's going to begin to fall, right? Now, again, this is the whole idea with the gun. Whether I drop that dart and it falls straight down, or if I throw it horizontally, gravity doesn't matter, okay? It's still going to accelerate at the exact same rate falling down, okay? Home run deer. So what you're told is that the dart hits the board 0.22 meters below the height from which it was thrown. So that's the vertical distance that it fell. It's about 0.22 meters is about like yay, okay? So I threw this thing at the exact center of the dart. I threw it at the center of the dartboard, bullseye. But it went down like this. So that 0.22 meters here is equivalent to the 41 meter height of the Acapulco divers that you just worked. Okay, it's the exact same concept. Now, so in this one, because you know that, you know how far it falls, what can you determine?
Time.
How long it's in the air. Okay, using the exact same equation that you just did. So once you get time, then you can go how far from the board was it launched. Well, you know, range equals Vx times time. You have your Vx, your 12.4, multiply that by the time it's in the air, that's how far back
Is
you
it
are.
like a really, really, really small time?
Yeah, I mean
Okay.
it only falls like this far.
Okay.
So it's like if I hold this up and I drop it, it's a very, very small amount of time that it's in the air. Yes, Eric.
How many forces and acceleration vectors should we have on the front?
However many forces there are and however many accelerations there are. That's all I'm going to tell you.
All right.
That's all I'm going to tell you. Make sure on problem number 1 on that back side, when it's talking about, like on that first one, I'm going to double the horizontal velocity. Do not just say, oh, it's going to get bigger, oh, it's going to get smaller, okay? You can answer that one of 2 ways. You can either say, hey, it's going to double, it's going to triple, it's going to increase by the square root of 17, okay? Number 1 on the back there towards the bottom of where you have to say how it changes. Or you can actually do the smash mouth physics and go back and recalculate everything. Okay? If you're going to do the smash mouth physics, I want to see the numbers. Okay? So, I don't care. Now, let's talk about problem number 2. How many significant digits should all of your answers have on problem number 2? 3. Okay? They should have 3 significant digits. 0.4 is not 3 significant digits. Okay? So, just saying. Basically, every answer on 1 through 5 on the back should have at least 3 significant digits on all of them, because all of the values that you have 3 significant digits. Okay. Make sure on 6 and 7 on the front that you have indicated which one is the ball that's rolled and which one is the ball that is dropped. Okay, just don't draw lines on that and think that I'm going to know what you have. Bad. Bad. Okay. Anything else? Going once, going twice. So,
Is there, because like, it wouldn't be a horizontal
Get that in
acceleration. The velocity stays the same.
Yeah, I think we'll just see.
all right. So, here's the next thing that we have, and this is actually, now we're going to make it a little bit more complicated because now we're going to deal with ground-to-ground problems. So, when this marble gets launched, let's say that I set it like a 60-degree angle, okay? So, when this thing comes out of this launch, okay, so visualize this. Like, let's say my hand represents the velocity of the marble. So, the first thing that we're going to do is that we have to realize that when this thing comes out, it has 2 components to it. It's going to have a horizontal velocity to it, and it's also going to have a vertical velocity to it. So the first thing that we have to do is, technically, it's called deconstructing the vector, which is a really nerdy term for saying find the x and y components to it. So if I launch this, okay, Josh, get ready to catch this, okay? So if I launch this, right?
Ooh, nice catch, man.
Nice catch. Good hands. For a runner, that was a good catch. Okay.
For a runner.
Now, so when that thing took off, it has a certain amount of horizontal velocity to it. What are we going to assume happens to the horizontal velocity? Stays the same. So we're assuming that there's no horizontal forces acting on the system. Now, if I launched it, and theoretically, let's say I could shut off gravity during the path of the marble, just right through here. If I launch it and I shut off gravity, what would the path of the marble be?
Straight up.
Yeah, it would just go in, like, imagine that there was a line or a string from this up to the ceiling. So it would go on a straight line all the way up to the ceiling, because then it would not accelerate vertically, nor would it accelerate horizontally. But there is gravity. So the gravity is going to cause an acceleration only in the y, not in the x. Beautiful. Okay, so keep that in mind. So when you get a problem like this, and you're going to get problems like this. So I'm going to launch this thing at, let's say, 20 meters per second at an angle of 30 degrees. So here's the very first thing that you have to do. Here's the very first thing that you have to do. Don't pass go. Do not collect $200. Do not do anything. So the first thing you have to do is you have to find Vx and that initial vertical velocity. That is the very first thing that you have to do. Do not do anything else. Only do this. So, Mr. Gilchrist, how can I find the vertical component of my velocity?
Sine.
Okay, sine of
60 degrees.
times 20. So somebody take the sine of 60 times 20. This is old school. You should not have to think too much about this step.
17.32.
So call it 17.3 meters per second. And then my Vx should be 10 meters per second. Okay? Now, as soon as you get these numbers, never speak of that 20 again. It is dead to you. Okay? Don't use it again. It's gone. This is just a gateway vector to get these. That's all it is. So don't ever, 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 ever use that 20 again. It's done. Okay? Don't try and go, oh, that's my initial velocity. No. It was your initial speed that got you Vx and Vy, but that's it. Now it's done. Never, ever, ever speak of it again. It's goners. Now, I want you to pretend that this is no longer here. Boom, gone. So,
Well, it's no longer there.
now, pretend that you're back in the acceleration unit. And I'm going to tell you that I'm going to launch something straight up in the air with a velocity of 17.6 meters per second. So the first thing I want to figure out is the time up. Okay? So here's my question. Okay? Before you do anything else. Ellie, is my time up going to be more than 1 second or less than 1 second?
Yes.
Why?
Because it's greater than 9.8
Yeah.
meters per second.
Yeah.
So it's going to take less time to travel. I don't know. I'm confusing myself.
Liz, more than a second or less than a second to reach maximum height?
I think more.
You think more. Why do you think more?
Because if you take that number, divide by 9.8, it would be 1 is more than 1.
Okay? So look at it this way. What if my initial velocity was exactly 9.8 meters per second? How long would it take to get to a maximum height?
1 second.
Exactly 1 second. So since this is greater than 9.8 meters per second, and my time has to be greater than 1 second. So what you could do is that you could look at this from a perspective of velocity time graph. So I'm going to start up here at 17.6 meters per second. What's going to be the slope of the line? Negative 9.8 meters per second squared. Okay? So negative 9.8 meters per second squared. Because once it leaves the ground, the only force acting on it is gravity. Okay? There's no upward force pushing it up. Okay? All right? It just wants to maintain whatever velocity that it has because of inertia. So, knowing this, when I reach that maximum height, I can sit here and go, oh, okay, yeah, that's going to be 0 meters per second. So if you want to kind of go the route that Ellie indirectly talked about, and you go, oh, A equals V minus V naught over time, you know the acceleration. Yeah. You know the initial velocity. You know the final velocity. The only thing you don't know is time. So, okay, yeah. 0 minus 17.6 meters per second. So somebody do the math. Let's take 17.6 divided by 9.8. Should get
795.
So call 1.80 seconds. Right?
Right.
So it's going to take 1.80 seconds to go up. So if it takes 1.80 seconds to go up, it's going to take
More than 1 second.
more than 1 second. And how long is it going to take to come back down? Same amount of time, right? So my total, so at this point, I'm at 1.80 seconds. My velocity, my vertical velocity is 0. I'm at the top of the flight, right?
Right.
Could I use the velocity time graph at this point to find my maximum height? Brooklyn. Yes, what would I do? Find what? Yeah, which would be the area. So I got 1.8 seconds times 17.6, take half of that, boom. I can find my maximum height that way. If I wanted to go that route, that would be a cool thing to do. But if my time is wrong, that maximum height is going to be wrong. Okay? So is there a way that I can find the maximum height without using time? Howie, what could I do? That equation. So the other thing I could do is I could go v squared equals v naught squared plus 2ax. I know my final velocity, I know my initial velocity, I know my acceleration. The only thing I don't know is the height. There's a third option that I could use to find my maximum height. What's that? It's the one that's like a function equation where you can plug in time and initial velocity. Ms. Treadway. X equals? Huh?
Just a function of the equation?
Well, yeah, it's the only one that's really a function equation where you have time and initial velocity and acceleration.
V equals V naught plus AT.
No.
There's no displacement in that. I'm confused.
X equals 1/2 AT squared plus V naught time?
Yeah.
Yeah, let's look at that.
Quadratic, right.
So the other option that you could do is that you could use X equals 1/2 AT squared plus V naught time. Now the beauty of this is, and you're going to use this a lot with projectile motion, okay, this is a cool deal, because you got 1/2. Now, Mr. Taylor, listen to me. If you're going to use this, this has to be negative 9.8 meters per second squared, okay? Because that's the slope of the line. Then I can plug in 1.80 seconds squared plus the, what was it, 17.8 meters per second times. Okay? So here's the deal. Here's the beauty of this, is that I can find the height at any point. So if I want to find it at the maximum height, I'm going to use the time when it's at its maximum height. If I want to figure out how high it is 1 second into the flight, I plug in 1 second. But here's what you have to be very, very cognizant of. This initial velocity is only the vertical velocity. Okay? It's not the launch velocity of 20 meters per second. And here's the reason why. If you plug in that launch velocity of 20 meters per second here, then you're going to say that no matter what angle I launch this thing at, I'm always going to get the same maximum height regardless of anything else. Okay? So this is why it's only the vertical velocity, that initial vertical velocity, that gets plugged into here. That's it, nothing else. Now, so this is cool. You can do this, but you've got to plug in the time when it's at its maximum height. It's a cool deal. You can use this. It's grand. So the disadvantage of that equation is that it only works at maximum height. Okay? The advantage of this is that you're not dependent upon time. The advantage of this one is that you can plug in any value of time to get how high it is. The disadvantage is that if you drive your time and your time is wrong, then your maximum height is wrong. Okay? But it's a personal preference thing. So this is like the Swiss Army knife because you can plug in any value of time and get a height. Okay? This one's, that equation is cool. Okay? You can use the graph if you want, if you happen to have the graph. But again, mathematically, this is the easiest because it's 1/2 base times height. But again, that only works when you're at that maximum height, and that's assuming that your time is right. So, I don't care. Okay? I don't care. But notice, here's one commonality of all of these, that the one thing we didn't use was the 20 meters per second. What are you doing?
I was just coming here to hang out with you.
Okay, all right. Well, hang out, become. Okay, so the one thing that we did not use was the 20 meters per second. We only used that to find Vx and Vy. That's it. Nothing else. Never speak of it again. Okay, so if it took 1.8 seconds to reach the maximum height, hark pray tell, what is the total flight time going to be? 3.6, right? So it's going to take a total time of 3.6 seconds, okay? Now, knowing this, how far is the ball going to travel? What can I do to find out how far the ball is going to travel? Don't make this difficult.
Multiply time by horizontal velocity, whatever.
Vx?
Yes.
Okay? So here's the deal. If I know my Vx is 10 meters per second, then if I want to figure out how far it's traveled at any point in here, I'm just going to multiply Vx by whatever value of time that I have. So if I want to figure out how far it's traveled horizontally when it's at its maximum height, I'm going to plug in 1.8, I'm going to take 1.8 seconds times 10, I'm going to get 18 meters. If I want to know how far it's traveled when it lands, assuming that it lands back at that same point, I'm going to take 3.6 times 10 and get 36. Okay? So, remember, your horizontal velocity time graph is going to look like, what's your Vx time graph going to look like? Kendra?
Why do you always call me when I have this face, this expression on my
Okay,
face?
I don't even have my glasses on.
I know.
cannot tell.
I always, every time that I look up and I have a confused expression on my face, you always call on me.
Okay.
What did you ask?
Okay.
I would have gotten crucified.
Yeah. So, Kendra.
Okay.
Okay, you ready?
Yes.
Here's the question.
The Marvel fans.
No. I'm going to draw a velocity time graph
Okay.
for the horizontal velocity only. Okay?
Yes.
So here's my question. What's my Vx versus time graph going to look like?
Isn't Vx constant?
It is.
So it's a horizontal line.
It is.
Thank you.
At
10 meters per second.
beautiful. Okay? So it wasn't even that tough.
I know, but I wasn't paying attention. And I just and I just looked up, and then all of a sudden you go, Kendra. I was like, I don't know what you just asked me.
Okay. I really didn't pick on you just because you had a confused look on your face. I don't have my glasses on, so yeah, okay. So here's the whole idea, okay, and this is the big picture. Basically, this is a rectangle. When we say range equals Vx time, all this, when you look at range equals Vx time, all that is area equals length times width. That's all it is. This is just the area of a rectangle. And it works that way because our horizontal velocity is constant. So we know the length, whatever time we have, 3.6 seconds if it's the entire time. The width is the 10 meters per second. The area is the range. That's it. Okay? It is a linear function, but all this is, range equals Vx time, is a jacked up way of saying, oh, here's the area of a rectangle and its length times width. That's all it is. Okay? Now, I can't do that on the vertical velocity time graph because of the fact that the slope is not 0. It's slowing down and then it's speeding up. Okay? Good with that. Okay? Now, if you want to look at this in terms of how things change. So we said the Vx was 10 meters per second. So at this point, we're at 10 meters per second. So once it starts to fall down, what happens to these horizontal velocity vectors? Sam. Once it starts on the way down, what happens to my Vx?
Nothing.
Nothing, because we said the Vx was constant, right? Okay?
That's a trick question.
You kind of had, I think, a kindred look on your face.
Because he said when he was going down. So
It was a trick question, that's my job.
You do that on your multiple choice answer.
Yes, I do.
And the true
You're
false.
right.
You award those.
No, I don't.
Yes. Ask anyone.
There was the like one that was funny one I think.
dude, the multiple choice. The multiple choice.
Multiple choice always gets me somehow. I just think about them too
No,
much.
not good.
I'm like,
Should be the
what is
easiest.
it?
How difficult are multiple choice questions in college?
I heard about
Really hard. I'm probably gonna die when I.
Okay, see, there you go. So I'm just trying to get used to it. Good answer.
It gets so much worse.
Okay, all right. And I'm nice because I give the answer.
You're so nice compared to.
See? See? Hmm? Okay. All right. Now, meat. Meat. On the way up, what happens to my vertical acceleration vectors? Okay? So what's my initial vertical acceleration? Negative what? Okay. When this thing is launched, okay, what's my initial vertical acceleration? Negative 9.8.
You had a Kendra moment there for a second.
So, as it goes up, this gets smaller.
No.
You just said.
No, at the time I switched places with Kendra.
Yes.
That was my fault.
You channeled your
You channeled your Kendra
Yes.
right there.
Okay.
You're inner confusing yourself until.
Okay. So as it goes up, what happens to my acceleration vector? It stays the same. Okay? So if you want to get fancy, you say A equals negative G. Now, on the way down, Kyle, what happens to my acceleration vector? Does it switch sign and become positive?
Are you talking about the acceleration?
Yes, my
Dude,
vertical
are you
acceleration
dumb?
vector.
Why are we
Still.
still going over this?
Because
It switches.
it switches.
Dude!
No, it doesn't. I just like to make you upset.
And what's the real answer, Kyle?
So the real answer, Kyle,
Dude, you're so red.
It doesn't switch.
It's
it
alright.
doesn't switch. Are you sure?
No, I'm not. But that's my.
That's your
like the only
educated
other
guess.
answer.
Yeah.
Really, the only thing it can do here, it's one of those 50-50 shots.
The funny part was you said you were messing with him, and because you knew you were wrong, but then like you had a 50-50 shot, and you just had to pick the other one.
Okay, Kyle, on the way up, what's making it slow down? Gravity. So on the way down, is gravity still the same value?
Yes.
So is the acceleration still the same value?
Don't listen to Eric over here. Eric, you're just playing the devil's advocate.
It's still the exact same value. A is still negative 9.8 meters per second squared.
Well, that's what I said.
This thing doesn't keep. You flip-flop more than Donald Trump on that answer.
Oh, you're right.
Stay down.
I think it's because of the hair. Okay. All right. Now,
Wait.
At the top of the flight, something unique happens with the acceleration vector and the horizontal velocity. So up at the top, up here, okay? As it's going up, what's happening to Vy?
It's slowing down.
You sure?
Yes. Yeah.
Okay. So this thing is going to start with some Vy, right? That's pointed up, right? And then on the way up, the Vy is going to get smaller and smaller and smaller, and then at the top it's going to hit 0. Now, at any point on here, and stay with me through the terminology, at any point on here, the speed, okay, the speed would be the resultant of these two vectors. So like at this point, my speed vector would be pointing like this. Here, my speed vector points like this. Here, my speed vector points like this. So as it goes up, my speed vector is going to get more and more shallow, right? So up at the top, what's the only velocity that it has? Horizontal. So notice at the top, this is the only point where your acceleration vector and your speed vector are at right angles to each other. Okay? Because up at the top, there is no vertical, it's only horizontal. This is the only point that it forms a right angle. Now, as it goes down, your speed vector gets bigger and it becomes more and more vertical. Okay? So you've got like this action going up, it's going to come over, brake, and then your speed vector is going to come down like this. If it launches with the speed of 20 meters per second, what's its speed when it lands, assuming that it comes back to that same point? Yeah, it's still going to land at 20 meters per second, because I'm asking you about the speed. So imagine that you've got a little radar gun down here, okay? So it would measure a speed of 20 meters per second. Your radar gun only measures speed. We got to use the trig to find the x and y components of it. Yes, Garfield?
Could you move a little bit to your left?
So, that's not a right angle over there?
Where?
No, up one. Yeah,
Here?
right there. That's not a right angle.
Okay, right angle with what? My x and y are
Okay.
right angles.
And up there, it's only your acceleration and...
Yes, because this is the only thing that you have. Now, if I launch the ball straight up, okay? If I launch the ball straight up, is my acceleration vector and my velocity vector ever at right angles to each other?
No.
No, they're always going to be what?
Up or down?
Yeah, they're always going to be parallel with each other. So because once I launch this thing straight up, my acceleration vector is just going to be g, and they're going to be parallel with each other. So only on projectile motion do you have a situation where your speed and your acceleration vectors are not parallel with each other. They're always going to be at an angle to each other. Okay? Makes sense. Good? Great. Now, if I wanted to, okay, let's figure out what the maximum height is. Okay? So somebody, through hook or by crook, somebody get me the maximum height. Oops, wrong one. So either use the area of the triangle, let's do that, that's going to be simple. So somebody take 0.9 times 17.6.
0.9 times 7. Oh, 7.
Times 17.6.
So keep round 17, 30.
15.8.
So 15.8 meters. Okay? Now, so here's my question. Here's my question. So if you do this, you should still get the same answer. So this height was, what did you say, 15.8
Yeah.
meters. So here's my question. This is occurring at 1.8 seconds into the flight, right? 1.8 seconds into the flight. I'm at a maximum height of 15.8 meters. Cool with this. Now here's my question. if I go to 0.9 seconds into the flight, okay, I'm going to go to 0.9 seconds into the flight. So let's just call this roughly 16, okay? So here's my question. At 0.9 seconds into the flight, is my height at 0.9 seconds into the flight going to be half of this, about 8? Is it going to be more than 8, like maybe 10 or 11? Or it will be less than 8, maybe 5 or 6?
Exactly.
So those are your three options. Less than 8, around 8, halfway, or more than 8, meaning, you know, it's going to be 11 or 12. So, how many vote A is going to be less than 8? Equal to 8, or half of the height. 1, 2. More than 8. Vast majority. Cubby, why did you vote more than 8?
Because during that time it's going to be accelerating at a faster speed. No, it isn't at all.
You can come back to our B. Join B with me.
It's going to be accelerating at a faster speed. What does that mean?
I don't know.
I don't know.
Wait,
I don't know.
I took that
We demand shrubbery. Okay?
just think you made it.
Did you ever have a reasoning class?
Austin.
He's not that smart.
Yes, Eric with the K.
Oh, that both are good. Can I say why it's?
Yeah.
Because it's not a linear function, it's kind of squared. So it's going like this, it's not this. If it was linear, it would be 8, but since it's not 8. It's more than 8.
Okay? I like your thought process. We know it can't be 8 because it's not a linear function. So that leaves us back to less than 8 or more than 8.
Well, it's traveling. Oh, I'm not going to say anything actually. I decided against it.
Okay, well let's just settle the argument. Okay? Now, the only way that we can settle this argument, and the only way we can settle this argument, is to use this equation, that x equals 1/2 at squared plus v naught time. This is the only way you can settle this, because you have a specific time. You cannot do this any other way. This is it. No other options. Mr. Taylor, what am I going to use for my acceleration? Never mind. Kendra, what am I going to use for my acceleration?
9.8.
No,
Yes, positive or negative?
Negative.
Yes.
I don't know.
See, I was paying attention that time.
Now,
0.9.
I want to put in half my total. I'm going to put in 0.9 seconds because I want to know how high it is at 0.9 seconds. Now, here's what you're going to do wrong. You're going to forget to square this time. Okay?
Okay, just put 0.81 right there now. Just do it.
Whatever works for you. And then don't put in the 20. Do not put in the 20. Do not put in the 20. Only put in the vertical component.
That's in your state.
17.6 meters per second times 0.9 seconds. So what do you get?
Wait,
11.9?
what just happened? What about your square?
Oh, that's the V naught.
Okay? So, about 12 meters, right? So if you think about it, and it's actually something that Eric said, because of the fact that it's a quadratic function, think about this. In 1 second, this is where you have to compare a linear function to a quadratic function. In 1 second, you are going to go from 17.9 meters per second, and you're going to slow down as a linear function. So you can take 17.6 minus 9.8, and you can get the velocity at that point. But you can't do that in keeping track of your position because of the fact that the time is squared. So if you think about it, in terms of like time, because you're going so much faster in that first second, it actually goes to harken something to you said there, Cubby. Okay? Because at the beginning you're going so much faster, in that 1 second you're going to travel more time. You're going to travel a greater distance in that first second than you are in the second second because you're going so much faster. So you were 3/4 of the way right, okay? Just the wording was a bit off, okay? Cool with that? Grant, got it? Okay, so stop that for a second.
Would you feel bad for
I'm
somebody?
gonna tell you something I'm really
Okay.
I am offended personally that you don't have the picture of me recording.
Okay, it was kind of pretty.
And it was the best.
Okay, you got to admit, it was a little pretty.
I mean, yeah, but where is it now?
Yes, I've got this back.
Oh, okay.
Yeah,
Yeah,
I've still
that's
got
alright.
it.
That's alright.
Yeah, it's just, I just don't have, and I still have it.
I've done something terribly wrong.
Okay. All right. So let me kind of get you through some of these problems. So on problem number 1, in honor of baseball, okay? So here's the situation on problem number 1. 2 different baseballs are going to be pitched. Both of them with nothing but horizontal velocity, okay? Nothing but horizontal velocity. They're both going to make it to the catcher, okay? So don't sit there and go, oh, the faster one travels further. They're both going to make it to the catcher, okay? So the question is why does the ball that is thrown faster tend to be in the strike zone, but the one that is thrown slower tends to be below the strike zone? Okay, so that's the question. When you get to question number 2, a Teflon puck with a mass of 0.1 kilograms slides on a frictionless surface. It's already moving.
Thank you.
Okay? Don't push it. It's already moving.
That should be a chant.
Don't push shit.
It's already moving. Don't push it.
That is so annoying.
Can I put this on the highlight reel?
That was you.
I'm totally going to get hired.
Oh, that was no.
You in there.
Okay. All right.
Little bird.
So, what you're going to do on problem number 2, there's a sequence of problems here. The first one that you're going to do is you're going to draw all the forces to scale with a ruler. Okay?
You hate us.
I really do. Did you just figure that out?
Yes.
Really?
I had
It took you 9 weeks?
Hey,
I figured it out.
Okay.
Second.
Do you hate all of your students or
All of them.
all of them?
Yes. It's tough love.
That's reassuring.
Okay? I could make this the easiest class in the world.
I wish you
That would be
I could.
that would be nice.
I could make it easy for you, and I can make it easy for me. I could say, hey, every assignment is like 2 problems. You get it done. They're easy. Everybody
And you
gets
don't
an
have to go
A,
to scale.
and bad things are going to happen. Okay.
Like what?
The end of the world.
Yes. So anyway, so you're going to draw the forces acting on the hockey puck while it's on the table, and then the forces acting on it after it has fallen off the table. Now, you see that 4th one right there above the ground? I've got a couple little asterisk notes there. It's not hit the ground yet, but basically you can slide a piece of paper in between the hockey puck and the table, right? So it hasn't hit the ground, but it's as close as it can be without actually hitting the ground, okay? Now, on B, you're going to draw acceleration vectors. But your acceleration vectors are going to be driven by what happens in the force vectors up above. If your force vectors cancel out, there is no acceleration. If your force vectors don't cancel out, then you have an acceleration. When you get to C, you're drawing velocity vectors. Now, it's moving at 5 meters per second, moving along. Then it's going to fall 0.6 meters, then it's going to fall 1.2 meters. I want the velocity vectors and the horizontal velocity vectors at each point, okay? So the easiest thing to do when it's falling is to assume that it just starts up there at 0 and falls for 0.6 and then work it again and treat it as it's fallen 1.2. That's the easiest way to approach that problem. On the back side, when you get to questions 5 and 6, you're going to hit a golf ball. It's going to leave the club face at 32 meters per second. The first one is going to be at an angle of 30 degrees. The second one is going to be at an angle of 60 degrees. Okay? I want the total flight time, the height, and the range for each one of those. When you get to number 8, let me explain what's happening on number 8. You're going to hit the golf ball,
Crazy, bro.
and it's going to go like this. Okay? So, you've got 40 meters per second at an angle of 60 degrees. So there's a whole bunch of things that I want. I want the range, the maximum height, the speed, and the angle. So on D, or on C, what is the speed of the ball when it lands? When this thing lands, it's going to have an X component and it's going to have a Y component. The only thing I want is the resultant of those two vectors. Okay? On C. Okay? Now, you're going to have to find like the maximum height. There's a whole bunch of stuff you're going to have to find to get that Vy. And you're going to have to find like the total flight time. It's going to be a fairly complicated problem.
Yay.
So, I'm done.
See your
You're on your own.